All right, welcome back to the afternoon session of day one. Our next speaker is the second invited speaker of this event. It's Mathieu Anel from Carnegie Mellon University. He's going to talk about the choice axioms and Postnikov completeness.
Thank you, Nima. I would like to thank the organizers for the invitation. I'm very happy to be here. I'm interacting with the HoTT community, but there's so many people in that community that I had never met, so this is a perfect occasion. So I'm a topos guy, an infinity topos guy, so I'm going to talk about infinity topos a bit. But I'm going to try to make a connection with logic. And so we stumble upon an interesting variation on the choice, on the axiom of choice with Reed Barton. Reed Barton, that was mentioned in Sina's talk. And we studied the problem of Postnikov completeness, and I'm going to talk a bit about that at the end. And we realized that we could prove certain criteria for Postnikov completeness by generalizing the axiom of countable choice. And so that's what I'm going to present today. I'm going to mostly give you a definition, and we're going to see examples where these axioms hold and or does not hold. And then in the end, I'm going to explain how we use it to prove criteria for Postnikov completeness. So I guess by now I'm a member of the HoTT community, but I don't talk the HoTT language. So I'm gonna talk the language of category theory. Apologies for that. So there's going to be diagrams, and there's no sigma, no pi, no dependency. You're going to see that the formulation of the axiom is internal, and so it makes sense internally. And actually, the main result that we have makes sense internally to a topos. But for the examples, I need to work externally, and so that's why I always work in category theory. So by category, will mean an infinity one category. So since infinity category contains everyone, I think it makes sense to simplify the terminology and to just talk about categories. And I'm not going to use any particular models, so I leave you the choice of your favorite model for infinity categories. I'm just going to pretend that infinity categories exist and work from there. So I'm going to talk about infinity topoi, but I'm going to talk about n topoi also for n lower or equal to infinity. And by this, I mean the notion that is defined in Leuven's book. So I'm not going to recall the axioms of an n topos, but one topos is, I'm going to need essentially the two extremes. So one topos is a classical notion of Grothendieck topos, and an infinity topos is the version of Leuven where it's a left exact localization of a prechief category, if you want, or a category with descent, etc. Then again, I won't recall the axiom. But if you have questions at some point, just raise your hand and I can give more details. So I'm going to use the concept of a surjection, which is my name for the effective epimorphism of Leuven. It's also a name for the -1 connected maps. And so I'm going to recall the notion of n-connected maps in a minute, but in our paper with Eric, we find it convenient to call them just surjections. So they can be defined as the maps that are left orthogonal to monomorphisms. And the orthogonality that I'm using here is the strict one, but the strict one in the higher setting. And it's also a map which is the quotient of the kernel equivalence relation associated to the map. So they're going to be important to define some notions. The important thing about surjection is that this is a purely internal notion. And I'm going to use the terminology, the HoTT terminology, by saying that an object in an n-topos is inhabited if the map to the terminal object is a surjection. Okay. So let me recall the axiom of countable choice. So the notion that I'm going to use is that a countable product of inhabited object is inhabited. And so I'm going to start to the one topos because it's a classical axiom in a one topos. So it can be shown, this statement can be shown to be equivalent to other more classical or more syntactical formulation of countable choice. Let me make a remark. So I'm going to work in, when I say topos and n-topos, I'm going to assume that there are presentable categories, so all colimits are around, and so I'm in a Grothendieck kind of topos paradigm. We can discuss in the end to see exactly which fragment of the structure of a topos I need for my proofs and my definitions. So, I mean, everything is going to go through in an elementary infinity topos, that's for sure. But it seems that we may need even less. And I mean, to state this axiom, we need way less. We don't need pi types, for example. So, I mean, we need countable products, but that's all. Okay, so let me draw some diagrams so that we can be sure that we understand the same thing by a sentence. So I have a family over the natural number object, and this is a surjection. So it's a family of inhabited object. And I take the product of my family, and I want it to be a surjection over the terminal object. And so concretely, this means that my original map has a section, but this section exists only locally over the terminal object. Sorry? Oh, did I make a mistake? Oh. N to A? No, this is... Are you talking about this map? No, I look at A as a family of objects indexed by N. Okay, so let's see examples of topoi satisfying the axiom of countable choice. So, I mean, the first one is sets. By sets, I mean classical sets. So much more is true, obviously. In sets because we can replace natural numbers by any object of set. Yeah, I'm a classical guy, sorry for that. And so we can also take any slice of the category of sets, which is the same as the power of sets, the I diagram of sets, where I is a set. Yeah, sorry, I forgot to say, in sets, an arbitrary product of surjection is always a surjection. That's what I meant. So we can have a group acting on sets, and this is again a setting where the countable choice axiom works. So in fact, we could take any pre-sheaf for a category, and that would also work because everything is computed term-wise on a pre-sheaf category. So it all amounts to computing in sets. Less trivial examples are sheaves over the counter space, or a sheaf over an Alexandrov space. And, yeah, I hesitated to remove that comment, but that's okay. So in an Alexandrov space, so basically you start with a poset, and you take the upper or lower sections of your poset depending on your origin. And the open subsets are closed under arbitrary intersection in that setting. And so you can prove that this, because of that, products, countable products have always, of inhabited objects are always inhabited. Oh, maybe I should say a bit what's the, I didn't prepare a slide for that, but let me try to explain. Let me try to go back quickly to the problem. Essentially, we want to produce a section of this. So producing a section of this, producing an element in all those AN, in the various AN. And so in a topos, certainly all AN have local sections, but those local sections may not exist on the same domain. And so if I think of my terminal object as some space, and I think of sheaves over a space, all my objects admit a local section around a point, but the neighborhood of those sections can become smaller and smaller. And that would be okay if I had only a finite product, because a finite intersection of neighborhood is a neighborhood. But as soon as I have a countable product of objects, I need to take a countable product of neighborhood, and this might not be a neighborhood. But in an Alexandrov space, it is. So that's why Alexandrov spaces satisfy the axiom of countable choice. Actually, they would satisfy the axiom of arbitrary choice. And also, you can recognize the condition as a sort of a projectivity condition on N. So in any topos where the natural number object is projective, will satisfy the axiom of countable choice. Actually, the statement of the axiom of countable choice is exactly saying that the natural number object is internally projective. Now, a counterexample. And the easiest counterexample is probably sheaves over the real interval. And so I'm going to try to explain what's happening. So this is happening exactly what I was saying before. So we're going to take, it's possible to find a family. So I'm going to construct a countable product of objects, of inhabited object there that doesn't have any section. Actually, the product is going to be empty. So for this, I start with choosing a cover of my interval by open subsets of diameter less than 1/k. So that's always possible. And then we have a family of cover like this that becomes smaller and smaller. And so I take the union of all those guys. Oh, sorry, that shouldn't be an alpha here. It should be it should be an n. Oh, no, okay. Ooh, lots of mistakes. Sorry, this should be a k, because I want the k to index the size of the cover. So it's supposed to index my objects, and this should be an n. So anyway, this is a surjection of my interval, and so it's family of inhabited objects. But now, if I consider the product is empty, because if I look around the point x, if I want to build a section of each of the AN, well, eventually, so I fix a neighborhood of my section, but the pieces are becoming smaller and smaller and smaller, and so there's no neighborhood of x where my thing is going to have a section. So because of that, that's the external proof that the thing is empty. Question? Yes? No, well, I mean, you need the diameters of the cover to become smaller and smaller and smaller. Otherwise, they could still have some local section. And so, I mean, the fact that the product is empty is the more drastic counterexample that you can think of, because clearly there's going to be no way to map into that thing. But you could imagine that with arbitrary, I mean, this product doesn't have to be empty for the thing to fail. I don't know if this was your question, but okay. So this axioms was stated in the case of a one topos, but clearly makes sense in the higher setting, because in an n topos we have a notion of surjection also, and so we can ask that a countable product of surjection is again a surjection. So in particular, it makes sense for n equal infinity. But in the higher setting, we're going to see that we can introduce some homotopical variation of this axiom. And so we're going to use the notion of connected map instead of the notion of surjection to formulate those higher axioms. So I need to recall some notations and some terminology. If I have a map from A to B in my n topos, I define the diagonal by the usual formula. So it's also the family of all identity types of the fibers, sorry, of the space B indexed by the object of A. And then I define the hierarchy of diagonals. So I start with 0, that's the map itself, and then I define the iterated diagonal. And then, using this iterated diagonal, I can define that the condition for a map to be M truncated if the M+2 diagonal is an isomorphism. And I hope I have the index right. And so, example, if I look at the -1 truncated map, this is the same thing as a monomorphism. So let's see if I have it right. So m plus 2, so minus 1 plus 2, that's 1, so that should be the diagonal of f is an isomorphism. That's indeed the definition of a monomorphism. Good for me. And once we have this notion of m-truncated maps, we can extract the category of m-truncated object, and I'm going to denote it like E truncated by m. And this is a reflective subcategory. The reflection is the m truncation. And this is an m plus 1 topos. And hopefully here's also I have the index right. So the 0 truncated object from a 1 topos, so yeah, that's okay. Sorry? Oh, in my setting, yes, because I'm working with presentable categories, and so there's you can show that this is a category of local objects actually for a single map for the sphere mapping into the point, and so the reflection will always exist by a small object argument. Now the notion of m-connected maps. So, oh, sorry, yeah, I forgot to underline this. So I'm going to denote Tm, the class of m-truncated maps. And so the notion of m-connected maps also can be defined using surjections. And the condition is that all the diagonals have to be surjections up to m plus 1. And let's verify the degree of the indices. So if a minus 1 connected map should be exactly the same thing as a surjection, and so we should have only a condition for k equals 0, and if m is minus 1, we get indeed k equals 0. And so now we have the pair of m-connected maps and m-truncated maps, and they form a modality. This is the category theoretical way of dealing with modalities as a factorization system which is stable by base change. And so every map can be factored like this. Okay, I assume you've seen that. Now, here is something a bit more interesting, is we can also define the notion of infinity connected maps, which is a map which is m connected for every m. So it's all the diagonals of m are surjections, all of them. And infinity connected maps comes with a notion of infinity truncated maps, which cannot be defined using the diagonal. And the only way they can be defined is as being orthogonal to infinitely connected map. So I'm going to use this terminology infinitely truncated, which is not standard, and Lurie uses hypercomplete. And so they are not truncated map at all. And they are somehow generated by all the truncated maps, but in a bizarre way, so I'm not going to expand on that. And again, we have a modality where the infinity connected maps and the infinity truncated maps. And we have a subcategory of infinity truncated object, which is also known as the hypercompletion of the original topos. So I said that I'm going to work on n topos for variable n. And so if n is not infinity, those notions are completely trivial. And this notion becomes an invertible map, and this becomes the class of all maps. And a good thing about the category of infinity truncated object that it is again an infinity topos. So now let's go back to our choice times axioms. So we're going to need a variable d. D is for dimension. And we're going to introduce a countable choice axiom of dimension lower than d. So I'm going to say CCD for short, because this is too long. And so it can be defined in any n topos, and no need to impose a relation between n and d. We're going to see that some of the axioms are going to be trivial depending on n. And here is the axiom, is that a countable product of d minus 1 connected object is inhabited. So I'm considering product of highly connected guy, but in the end, I don't ask for connectivity at all. I just ask that the thing is merely inhabited. So countable product, the countable products have a loss in connectivity. And so we can reformulate this axiom in various ways. So first of all, I can, instead of working only with D-1 connected object, I can take any highly connected object, and the condition is equivalent to imposing that for any n, the product of n plus d connected object is n connected. So the condition for n equal -1 imply the higher condition. Oh, sorry, this n has nothing to do with this one. Yeah, I should have changed that. Instead of working with objects, I can also work with maps, which is what I'm going to need. So this statement is internal, but it is in fact equivalent to the external version where a countable product of D-connected maps are surjections. And again, I can replace my D-connect. Oh, sorry, there should be a D-1 here. And that's equivalent, again, to n plus D connected maps are sent to n connected maps by countable products. So now that we have a definition, we need to find examples to see that this axiom is sound and interesting. Oh, yes. Sorry, here is the strength between the various axiom. The axiom of dimension D-1 is the strongest. It actually is so strong that it says that a countable product of arbitrary map is a surjection. So that collapses the whole topos into a single object. So this is not an interesting axiom. CC0 is the usual countable choice axioms. It says that a countable product of -1 connected object is inhabited. So that's the version we saw before. And then we have CC1, CC2, etc., and some axioms CC infinity, which is the weakest. So yeah, that's what I just said. That the only n topos that has CC-1 axiom is the trivial topos. So if S is S lower than n, this is my notation for the category of n truncated spaces. And so this one has CC0. So we saw that with sets, and the same property happened with spaces, that an arbitrary product of surjection in spaces is a surjection again. And that's for the same reason in sets. That's because the axiom of choice holds. And so, or another way to understand also to prove this result is to say that, the category of spaces does enough projective objects. And the projective objects are exactly the sets. And every object can be covered by a set. So there's enough projective object in that sense. And then again, something much stronger happened is that I could have considered arbitrary discrete product, and there would still be surjections. But I cannot improve this to arbitrary product. If I take products indexed by groupoids, by non-discrete spaces, then this fails completely. And I mean, actually, the product need to be indexed by projective objects. That's the way the surjection works. So because this is true in the category of n-truncated spaces, this is true in any diagram of n-truncated spaces. And so for any category C, we have CC0. So this includes the case of a slice of the category of n-truncated spaces. If I have a one topos, the axiom CC2 is trivial, because the class of one connected maps is reduced to isomorphism, and product of an arbitrary product of isomorphism is always an isomorphism. So the condition is trivial for this one. So in a one topos, is this CC2? No, sorry, that should be CC1. Oh, now. Oh, I think I made a mistake in my indexing here. So the only axiom interesting in a one topos is CC0. So that should be a CC1 here. And that should be 0 connected and not 1 connected. Ooh, I need to correct that. But now that we have higher topos, we're going to see that some nice. Oh, sorry. So the generalization of this is that in an n-topos, there again, I got it wrong. Okay, well, there has to be a point where some indices like this had to be wrong. So in an n-topos, the sufficiently high dimensional countable choice axiom always hold. But here is the interesting thing. We could think, because of that, we could think that this infinity holds in any infinity topos, but it does not. And we're going to see a kind of example. And, but every hypercomplete infinity topos does have CC infinity by trivial reason, because infinity connect. So CC infinity. Let me go back to the statement. I forgot to underline this, but yep. Oh, sorry, where it is. So CC infinity says that a countable product of infinitely connected object is inhabited. So that's an interesting condition. And so when in a hypercomplete infinity topos, the infinitely connected objects are all contractible, and so obviously their product is inhabited. And if the countable choice axiom holds in some n-topos, it holds in the truncation also. And so in particular, if some countable choice axiom hold in an infinity topos, it will hold in the hypercompletion. So let me review. How am I doing on time? So let me sketch an example of an infinity of an infinity topos without the axiom CC infinity. So this is typical of topos theory. You're trying to look for a counterexample of something. Just take the topos classifying the thing. And so we need a countable product of infinitely connected object. We're going to consider the topos classifying a countable family of infinitely connected object. And so first of all, we need to know that such a topos exists. So the notion of infinity connected object is a geometric notion. So there is a classifying topos for that. And a reason is if I want to define my C-infinity condition, all the diagonals have to be surjective, and that amounts to impose that some monomorphisms are invertible, and that's a Grothendieck topology. So I can do that. So here is the topos classifying infinitely connected objects. This is going to be my notation, S bracket X infinity. And so this is just a subcategory of functors from finite spaces to all spaces, and I take the sheaves for the atomic topology. So I'm forcing every map between representable to be a surjection. And the universal infinity connected object is the sheafification of the canonical inclusion of finite spaces in spaces. And okay, so forget about this. That's just reformulating what I said. And so now here is the fact that we're going to need is that there exists infinity connected object with an empty space of global section. So let's assume that for now. And so as a functor X infinity, it sends the empty space to the empty space. Yes? Oh, the atomic topology that's my name for the topology forcing every map between representable to become a surjection. So you take the collection of images of all those maps, that's a collection of monos, and it generates a Grothendieck topology, and that's what it is. So this is my justification for the fact that we can find infinitely connected object without any global section, but let me skip that. And now let me go back to my example. Now I'm doing the same thing. I'm classifying a countable family of infinitely connected objects. And now this is a subtopos of the topos of fin to the n in two spaces. And so this is just, as a category, this is just a countable family of finite spaces, all of which are, almost all of which are empty. And then there's an atomic topology in each variable of this. If I think of this as functors of many variables, I can impose the atomic topology in each variable. And here is the fact, is that the product of this guy is empty. And the proof is just using the previous lemma. So each object, the values infinity object as a functor from this category to spaces is just first a projection onto the n factor, and then I use the universal infinity connected object. And so if I evaluate a product, the product of all those objects on some space in fin n, some of the value has to be empty, because eventually all of the AI, some of them are going to be empty, and so then we have an x infinity of empty, and that's empty, so everything is empty. So CC infinity is a non-trivial axiom. So to get more examples, I need to say a few words about homotopical dimension. So let me skip this a bit, because I think it's going to be technical. And so there's a notion of homotopy dimension introduced by Lurie in his book, and we can use that as a condition. This is a non-trivial condition for a topos. It's a generalization of a notion of projective objects. A projective object is going to be the notion of an object of dimension of homotopy dimension 0. And if we replace the class of surjection by the class of D connected map, we get the notion of object of homotopy dimension D. And so that's the result that we need. So we get more examples of axioms CC of dimension D by looking at a topos with enough object of homotopy dimension D. So that includes the spaces that are locally of dimension D. And so typically, our interval, we saw that doesn't have CC0, but it has CC1. So that means that the failure that we had before, so a countable product of inhabited object may not be inhabited, but a countable product of connected object is always inhabited. So it's not far from satisfying some, I mean, it has some version of axiom of choice is holding in that thing. And if I take the cube of dimension D, then we can prove that it has the axiom, the countable choice axiom of dimension D, but not CC D minus 1. So all those axioms are different. And if we are clever and we take the coproduct of all those guys, we get something that has CC infinity, but that doesn't have any CCD for a finite D. Okay, how much time do I have to? Oh, that's the coproduct as a geometric in a geometric category. So it's the product at the level of categories here. Sorry, 10? 10, okay. So I had an argument to explain why this has as the axiom CC1. So let me sketch it, because I think it's interesting. So I explained the failure of CC0 because we were not able to find local sections of a product, of a countable product. But if the objects are inhabited, actually we can produce such a section. So here is the argument. So I'm going to fix a neighborhood of a point in my interval. It could be the whole interval, actually. And then if I have a family of objects, so each object has local sections, but maybe not on U, but locally on U. So there exists a cover of U where I can have my global section. And we can, in fact, refine the UI such that the two local sections are oh, I should, yeah, sorry, I think, yeah, I'm not going to be very clear. I'm hesitating to draw a picture. Okay, you know what? Let me skip this example. Sorry for that, and I'm going to move on to the talk, and I'll try to come back about this to explain this at the end. So because I want to say a word about an application, which was the motivation for introducing these axioms. So we were with Reed, we were looking into the so-called condition of Postnikov completeness for an infinity topos, and there was a paper by Mondal and Reinecker from 2022 where they prove they essentially prove that if a topos satisfies the axiom of dependent choice, which say that a tower of surjection is again a surjection, then they could deduce some Postnikov completeness results. And so we try to understand the proof and come up with a simplification of the proof. And so we have our result actually holds for with a weaker assumption of countable choice only. And so I'm going to explain this statement. And so we can prove that if countable choice of dimension d for a finite d doesn't work for C infinity, for d equal infinity, then every formal Postnikov tower is an actual Postnikov tower. And so I'm going to spend some time explaining this. So we saw that the category of n truncated object is reflective, and I'm going to call Pn the reflection. And then we have, in fact, a tower of categories. And the infinity truncations sit at the top. And I'm introducing the Postnikov completion of E as the limit of all those guys. So actually, the infinity truncation is going to have a morphism to this category, a functor. And so first of all, this is again a topos. So that's a bit, that's an interesting result because none of those guys is an infinity topos. And so this is actually an infinity topos. And the object of this category is the object of a limit computed in cat. So it's a limit of categories. And so the objects are just exactly the diagrams of the same shape. But now all the maps have to be are highly and highly connected. And so this looks a lot like the Postnikov tower of an object, but we don't know whether it comes from an actual object existing in E or not. And so that's what the theorem is going to say, is that if the countable choice axiom of dimension D holds, then every such formal tower is actually the tower of some object existing in E. So I'm going to introduce some terminology. So we have an adjunction between E and its Postnikov completion. So the first functor sends an object to its Postnikov tower, so the tower of all truncations, and the right adjoint is simply taking the limit of the tower. And so the topos E is said to be Postnikov complete if this, oops, sorry, I shouldn't have written this. I meant if this adjunction is an equivalence. And as useful, it's as often it's useful to decompose this condition into two conditions, which are the fully faithfulness of both functors. And so I'm going to say that my infinity topos is Postnikov effective if the map from E to post is a localization, meaning the right adjoint is fully faithful. So the limit functor is fully faithful. And that's equivalent to say that every formal Postnikov tower is the Postnikov tower of its limit. So I compute the limit, and then I take the K truncation, and I get back the stages of my tower. And I'm going to say that E is Postnikov convergent if this is the other condition, if the functor sending an object to the Postnikov tower is fully faithful. So E becomes a co-localization of the category of towers. And this is equivalent to saying that the limit of the Postnikov tower of X is X itself. So those two conditions are just the unit and the co-unit of this adjunction. And so here is the reformulation of the theorem, is that if CCD holds for a finite D, then E is Postnikov effective. And so as such, this is a statement that makes sense in HoTT. And we actually have Owen Milner. Owen, where is Owen? Okay, here is Owen in the middle, in the back. And Owen is working on the formalization of this statement. So yeah, so concretely that says that for every formal Postnikov tower, I compute the limit, and then I take the K truncation, and I get back my tower. So another way to understand this result, an equivalent formulation, is to say that the hypercompletion of the original topos is Postnikov complete. So E might not be Postnikov complete, but up to the hypercompletion, it becomes hypercomplete. And the two statements that E is Postnikov effective and the hypercompletion is Postnikov complete are equivalent statements. So let's have a look at the proof. Oh, yeah, sorry. Let me say that this is false for D infinity. There's examples of hypercomplete topoi which are not Postnikov complete. They are quite a bit involved examples, but nonetheless, they exist. And also the converse of the theorem is false, because the example that we saw for CC infinity is a counterexample. The hypercompletion of the topos classifying countable number of infinity connected object is actually the category of spaces. Because in the hypercompletion, we kill all the generators, we kill all those universal objects, so we are left only with constant sheaves. So the theorem is optimal in this sense. Okay, let me sketch the proof. You're going to see it's very simple. I have 3 slides, that's it. And it's a full proof. And so I start with a Postnikov tower, and I compute the limit. I call x the limit. And now I want to study the map from x to the k stages. And we need to show that this is k connected. That's the statement. Because we know that xk is k truncated, and so if this map is k connected, this has to be the k truncation. And so we're going to write this map as a limit of a tower of maps. So now I'm in the arrow category, and I'm looking at all the map from the higher stages above k into k. And they're all k connected. And so I have to compute this limit and show that this map is k connected. So you're going to see where you may have a feeling of where I'm going to use this axiom. So first, I'm going to reformulate this limit as an equalizer of a big countable products. So I take the product of all my maps, and then I use the arrow in the category n to produce 2 maps, and one of the maps is actually the identity. And now those products, they're going to be if I have an axiom CCD holding in my topos, this is a product of k connected maps, so they're going to lose d degree of connectivity. So all those products are k minus d connected maps. But since k, I can choose k arbitrarily high actually in the argument, and so this is always going to be a highly connected. And now, if I have 2 connected maps and I compute an equalizer between them, I lose 1 point of connectivity. If you think in terms of objects, I have 2 n-connected objects, and I take an equalizer. I need to involve the diagonal of my object, and the diagonal is 1 point of connectivity lower. So that's the thing. So my limit, the map at the limit is k minus d minus 1 connected under the axiom CCD. And so it's not, this is k truncated, so this is not exactly what I want, but I can truncate xk into xk minus d minus 1. And now the composite map from x to this one is k minus d minus 1 truncated. And so this guy is the k minus d minus 1 truncation of x. And since k was arbitrary, I can move it up, and I deduce that the whole tower is the tower of x. And yeah, and that's the proof. That's it. Very simple. And I think I'm out of time, so thank you very much.
All right, questions? Oh.
Okay. Would you mind saying again the proof of why this product of overall, and like in the classifying topos, why it's not CC
Ah,
infinity?
you want me to go back to the counterexample?
Yeah.
Yep.
Would you mind saying this again?
Yep. Okay, so at which point are you okay with the thing? You understand the construction of this guy?
Yep.
Okay. So you understand that each of the n-connected object is something like this? Okay. So now I want to compute this product. This product I can compute in a category of functors from fin to the n into s. And so this is a product of functors. So I evaluate at an object in this category. And what is an object in this category? It's a sequence of finite spaces which is eventually empty. And so I apply the definition of product of functors. So that's the first functor I evaluate at the first projection. So this is the first coordinate of A, the second, and etc. And eventually, the component of A become empty. And so I'm left with the value of the functor x infinity at the empty set. And this was the previous lemma that I could produce an infinity connected object with no global section. And if there exists infinity connected object with no global section, the universal infinity connected object cannot have any global section. Otherwise, all of them would have at least one global section. And so I can sketch the argument to construct such an object. Start with any infinity connected object in some topos which is not contractible. We know that exists. We have examples of that. Now, so it's not contractible. So that means that there exists an object Z in E such that the external mapping space from Z to X is not empty. And this is a space. This is not an object of E. And so because it's a non-empty space, oh, no, it's not non-empty. Sorry, I meant not the point. Made a mistake here. I want it to be not contractible, because that would be the definition of a terminal object. I want X to be not the terminal object. So this is not the terminal object of S. And so that means that in some pi n, there has to be at least two different elements. And so I can choose a better Z, and I can choose some Z cross some sphere such that this mapping space has at least two connected components. And then I changed my topos, I look at the slice over this guy, and I pull back my object X into some X prime. And now it has two different global sections. It is still infinitely connected. And it has two global sections which are not the same. So I take the path space between those two sections. So it's just the identity type between A and B of this infinitely connected object. And this cannot have any global sections, because if it had, then my two sections would be connected.
Thank you.
Other questions? I mean, let me ask a naive one. Why is it not reasonable to define CCD as just a product preserving the kind of connectedness level the way it does for like a one topos? Like, why is it this degree lowering thing that you defined? This is like
because there are examples of this condition. I mean, there would be another axiom.
I see.
And actually, there is this paper of Blas where I study the connection of choice axioms and cohomology. And he considered essentially the following axiom. He considered that a product indexed by an arbitrary set of connected object is connected. And so this is not an instance of my definition, because we don't start at the lowest level. We don't ask that it's homogeneous. It's a product of n of 0 connected is 0 connected, but we don't ask anything for -1 connected. So this is not my CC0 axiom. And actually, in his paper, he proved that this implies that this holds for inhabited things. So from the fact that a product of arbitrary connected object is connected, he is able to deduce that a product of inhabited object is inhabited. Now, the problem is that I don't understand the proof because I don't know the logical background that is using to do this proof. And clearly, I don't think this works in an arbitrary topos. And I do not know. I mean, that's actually, I think, a very good question to try to come up with a proof of this statement and to understand conditions that would imply this. The proof in the paper is that the axioms that every connected product of connected object is connected says that every tensor over a group is trivial. It's another interpretation of the axiom. And so every tensor has a global section. And so you can use this to construct global section for other objects, provided you can cover them by tensors. And that's essentially the proof. So it's working in a setting where it is true that every object can be covered by a tensor over a group. And I don't have a counterexample to this, but I don't have a proof that is always possible either.
Okay, thanks. Any other questions? Okay, then let's thank the speaker again.
Thank you.